continue our discussion on the typical properties of the solutions. There are many properties of solutions which are connected with this decrease of vapor pressure in the systems. So, they include relative lowering of vapor pressure of the solvent, depression of freezing point, elevation of boiling point, and osmotic pressure of the solution. All these things will decrease, and all these properties depend upon the number of solute particles irrespective of their nature relative to the total number of particles present in the solution. So, such properties are called as colligative properties. We are talking about vapor pressure of the solvent, relative lowering of the vapor pressure. We are talking about depression of freezing point. We are talking about elevation of boiling point. All these things are called as colligative properties because they depend upon the total number of solute particles irrespective of their nature. Okay. This is another property of the solution, and here I give a brief introduction to relative lowering of the vapor pressure. So, the vapor pressure of a solvent in solution is less than that of the pure solvent. Definitely this point you should appreciate now. So, Raoult established that the lowering of the vapor pressure depends only on the concentration of the solute particles, that is independent of their identity. That means, it is mainly dependent upon the solvent, irrespective of whatever you take a solvent, whatever you add a little bit. So, vapor pressure will come down. So, this equation establishes a relationship between vapor pressure and mole fraction of the solvent. So, here I write P1 is equal to x1 into P1 naught, very simple expression which we have seen earlier. So, the reduction in the vapor pressure is given as delta P1 should be P1 naught minus P1, because P1 will be lower than that because it contains solute. So, I can write this will be, I can write it as P1 x1. Here I have it, I am just substituting, and P1 0 I can take out, and what I have is 1 minus x1. Knowing that x2 should be x1 minus x1 because it is mole ratio, x2 is nothing but 1 minus 1. We can write delta P1 should be equal to x2 into P1 0. Okay. So, in a solution containing several non-volatile solutes, the lowering of the vapor pressure depends on the sum of the mole fraction of different solutes. So, we can write the equation something like this. In a solution containing several non-volatile solutes, the lowering of the vapor pressure depends upon the sum of the mole fractions of different solutions total. Suppose there is one component P1 and it will lower the boiling vapor pressure a little bit less. Another component is there P2, that also will lower to some extent. So, like that there will be different solutes that will lower the boiling vapor pressure of the substance, and that depends on the sum of the mole fractions of the different solutes. If suppose there are 2, then it is sum of 2 mole fractions. Then the equation, we can write the equation something like delta P1 by P1 naught is equal to P1 naught minus P1 divided by P1 naught, that should be equal to x square. You can P1 naught minus P1, that should be equal to N2 by N1 plus N2, number of molecules. It is same essentially, instead of writing concentration we are writing number of molecules, since x2 is nothing but N2 bar N1 plus N2. So, N1 and N2 are the number of moles of the solvent and solute respectively present in the solution. For dilute solutions, N2 should be much lower than N1. Hence, neglecting N2 in the denominator, we can neglect this N2 and then we can write P1 minus P1 naught minus P1 divided by P1 naught should be N2 by N1. This is because we are neglecting N2 in the denominator here. It should have been N2 because it is much lesser than N1. So, we can write this is N2 is nothing but W1 and W2 mass. We convert it into mass. W1 into a molecular weight 1 and masses of the solvent, and W2 are the W2 is the solute and its molecular weight. From this equation, knowing all other quantities, the molar mass of solute M2 can be calculated. That is, given any two substances binary system, you can determine the molar mass of a given solution just by measuring the vapor pressure of the solvent. Okay. Now, we go to another feature, that is essentially a colligative property, that is elevation of boiling point. Here also it is a similar system. The boiling point of a solution is always higher than that of the boiling point of the pure solvent, in which the solution is prepared as shown in the figure. Here I have a boiling point of the solvent, okay, top one, and this is the atmospheric pressure, vapor pressure, this is the temperature. So, I have a solution that is boiling point is given at this temperature. Okay. So, this is the boiling point of the solvent, but if I dissolve a substance, boiling point curve will go like this. So, where is the new boiling point now? It is Tb here, it is Tr here. So, there is a small increase in the boiling point of the mixture. Okay. So, this figure you should try to remember. So, similar to lowering of the vapor pressure, the elevation of boiling point also depends on the number of solute molecules rather than their nature. That is, irrespective of the nature of the chemical, whatever you put in a liquid, its boiling point will increase. So, it is you can find out whether a substance is a pure liquid or not pure liquid just by looking at the boiling point, is not it? So, boiling point will increase if anything is dissolved. Anything is dissolved means it is polluted, okay? It is different than the pure solvent. So, you can find out how much depending upon the increase in the boiling point, you can say how much has been dissolved. It may not tell you exactly what is dissolved, but the solvent is pure only to some extent, 98%, 2% is the elevation in boiling point, something like that we can estimate. So, a solution of 1 mole of sucrose in 1000 grams of water boils at 373.52 at 1 atmospheric pressure. This is a simple explanation, because water should boil at what temperature? 100 degree centigrade, no? So, 273 it should boil. Now, a solution of 1 mole of sucrose, if I dissolve it in warm water, what temperature it will boil? Instead of 373.00, it boils at 373.52 Kelvin at 1 atmospheric pressure. So, this is how we express K is Kelvin, degree Kelvin. Okay. So, look at the previous diagram now, this diagram. Here I have written Tb and Tb etc., Tr. So, delta Tb, that is increase in the boiling point of the solvent of a solution is Tb minus Tb naught. Okay. This is the solution and this is pure solvent. So, experiments have shown that for dilute solutions the elevation of boiling point is directly proportional to the molal concentration of the solute in a solution, that is so many grams of uh, the solute in so many kg. You remember our discussion. So, we can write delta Tb is proportional to the m, that is molal concentration. I can also write delta Tb should be equal to Kb into m. So, here m is the number of moles of solute dissolved in 1 kg of the solvent, and constant of proportionality Kb is called boiling point elevation constant or molal elevation constant. It is also known as ebullioscopic constant. The unit of Kb is so many kg per mole, okay, unit of Kb, degrees kg per mole. If W2 gram of the solute of solar mass M2 is dissolved in W1 gram, this is, I am trying to write an equation, then I can write M2 should be equal to 1000 into W2 into Kb into delta Tb divided by multiplied by W1 in the denominator. So, we have a similar experience of depression of freezing point. So, here what we have, similar to elevation of boiling point, depression of freezing point also happens. It is a common phenomenon. Lot of people who do not want ice to become solid, they add a little bit of salt into ice. So, especially in areas where there is lot of ice, snowfall, people do not want ice to fall on the roads. So, what they do is they keep on sprinkling salt, because the ice will melt and the freezing point will go down. So, when the freezing point goes down, the ice will melt a little bit and it will be more comfortable. It is a very common phenomena. So, depression of freezing point is a similar situation, that is irrespective of the nature of the substance, the boiling point, the freezing point decreases, boiling point increases and freezing point decreases. So, we can write an expression something like this, delta Tf is proportional to m. Similar exercise what we did for boiling point. Then we have delta Tf is equal to Kf, that is a constant, and I can write M2 should be equal to Kf into W2 into 1000 divided by delta Tf into W1. This is essentially similar equation like what we have seen for elevation of boiling point. So, it is also known as depression constant or molal depression constant or cryoscopic constant. Several names are available, and the unit of Kf should be kilogram degrees Kelvin per mole. Okay. So, here is an anti-elevated figure that shows you the depression of freezing point. It keeps on increasing as you keep on adding and a solute, and for a solution it is so much lower. Delta Tf is the depression of freezing point. Okay. So, for determining the molar mass of the solutes, we should know the quantities W1, W2 and delta Tf along with the molar freezing point. If we know all other things, the values of Kf and Kb depend on the nature of the solvent, and they can be ascertained from the following relations. What are the relations? These are the relations. Here the symbol R and M1 stand for the gas constant and the molar mass of the solvent, and Tf and Tb denote the, we have Tf here, we have Tb here, they denote the freezing point and the boiling point of the pure solvents in degree Kelvin, and further delta fusion, and here it is the change in the heat of fusion, and here it is change in the And now here we are talking about the boiling point. So, it is change in vaporization, delta vaporization, enthalpy of the vaporization. Here it is enthalpy of fusion. So, enthalpies of the fusion and vaporization of the temperature, these two equations will tell us exactly what is the problem. Now, we discuss another property that is known as osmosis and osmotic pressure. So, I have to explain a little bit about this to you. We are not going too much into details, but I will just give you a small intro. Okay. So, assume that we have only solvent molecules passing through semi-permeable membrane. I think most of you have heard of RO, reverse osmosis, correct? So, most of us, our houses have RO units available. What do they contain? They contain a semi-permeable membrane in which water will pass through and whatever is dissolved in water will not pass through. That is a semi-permeable membrane. Impermeable membrane means no water, no salt. Permeable membrane means everything will pass through. Semi-permeable membrane will preferentially allow the solvent to go through, holding the solute back. So, the theoretical basis is fairly simple. What happens is, assume that solvent molecule like water, it will pass through a membrane. So, if this membrane is placed between a solvent and the solution, the solvent molecules will flow through and solute molecules are held back in the solution. So, this process of flow is called as osmosis, very simple. Okay. So, flow of the solvent only. So, there is certain amount of pressure that is exerted during osmosis, that is known as osmotic pressure. So, osmotic pressure is proportional to the molarity of the solution at any given temperature, that is understood now. Okay. So, I can write pi is equal to CRT. Here in the slide I am writing pi is equal to CRT, concentration into RT, that is R is gas constant and pi is the osmotic pressure. Okay. T is temperature. So, I can write concentration as number of molecules divided by volume, right. So, pi should be equal to N2 by V into RT. So, V is the volume of the solution in liters containing N2 molecules of the solute and W grams of the solvent molar solute. M2 is present in the solution, then N2 would be W2 by M2. So, I can write M2 should be equal to W2 into RT by pi into V. So, the two solutions having the same atmospheric pressure at a given temperature are called as isotopic solutions. If there are two solutions having same osmotic pressure, then they are called as isotopic solutions. So, what is reverse osmosis? So, the direction of the osmosis can be reversed if I put a pressure larger than the osmotic pressure that is applied to the solution side. Now, imagine here I am drawing a picture of reverse osmosis and this is a SPM, semi-permeable membrane, and I have put salt water and osmotic pressure is there, and I put pressure on this solution and fresh water is allow fresh water on the other side. Okay. Now, normal osmosis, salt water will remain this side and fresh water will remain that side. So, only that much will go through, that is exerted by the osmotic pressure. Now, if I put additional pressure, then reverse osmosis occurs when a pressure larger than the osmotic pressure is applied. This will force the solution to go into this, but not the solvent, solutes. So, fresh water I am collecting this side, what remains here is more of the salt water that is remaining here. This is the principle of all ROs what we have in our houses, and this is how it will work. So, now the direction of the osmosis can be reversed if a pressure larger than the osmotic pressure is applied. So, the pure solvent flows out of the solution. Okay. Now, we want to talk about other properties of the electrolytic dissociation. Nearly 95% of the chemical reactions take place in aqueous solutions. You all agree with me now, isn't it? I am going to talk, I have mentioned several times now that 90% of this course discussion will be on aqueous solutions, and it is therefore necessary to have a general knowledge of the conditions which exist in such solutions. Let us make an attempt to understand basic concepts of chemical analysis using useful for electrochemical technology. What we are going to do? I am going to define again several terms, chemical terms associated with chemical reactions. So, I want to define an acid. What is an acid? Dissociation. Acid is defined as a substance. It gives a hydrogen molecule, hydrogen atom, ion sorry, in aqueous solution. So, an acid may be defined as hydrochloric acid or something like that, but its dissociation in aqueous solutions, it will dissociate as H plus and Cl minus, but it may also leave, because there are a lot of water molecules in HCl solutions. Okay. We write it as this H plus will react with one more molecule of water to give you H3O plus, that has got independent existence as an ion. H plus does not have an independent existence, but it will not remain like H plus. So, this is a very standard way of writing in all modern textbooks, that HCl dissociates to give you H plus and Cl minus, but we do not write HCl will dissociate and react with water to give you H3O plus, that is hydronium ion and chloride ion. So, it dissociates to give, we can also write this is a proton H plus. I can write acid is in equilibrium with proton and its conjugated base. What is a base? What remains if you take out the proton is base. Okay. Normally, our concept of base is that sodium carbonate is a base, sodium hydroxide is a base, potassium hydroxide is a base, calcium hydroxide is a base, like that. But we are extending the same definition, that acid is one in which a proton is there in along with its conjugate base in equilibrium with the undissociated acid. Some part of acid dissociates. So, it is also a tendency to lose a proton. This is the definition of acid from the Bronsted theory. Again, all this is PUC stuff, college chemistry, nothing much in this, and examples are BF3, AlCl3, BCl3, SO2 in an inert solvent. Here you can see that in HCl there is H plus, in acid there is proton, and proton is nothing but H plus, but in BF3 there is no hydrogen here, still it is an acidic solution. Similarly, aluminum chloride, BCl3, SO2, there are no protons here, correct. So, an acid, this is the definition of an acid, that is known as Lewis acid. This BF3, aluminum chloride, BCl3, these are all called as Lewis acid. Here we define acid as one which is which has got a tendency to lose to accept electrons, that is acid, that is Lewis acid, third one. Okay. So, we can similarly define what is base. A base is one which when dissolved in water should dissociate to give you a hydroxide ion. The other part, that is cation and anion. So, OH minus is anion, Na plus is cation. So, it may be, suppose it is KOH, then it will give K plus and OH minus. So, OH minus is very common in all bases, that is for normal day to day this thing. It exhibits a tendency to accept a proton, it need not dissociate. Okay. This is Bronsted concept. A base is one which can react with water to accept one hydrogen from here, NH3 will become NH4, because it is a proton it will be NH4 plus. And then once this loses H minus, H plus, what remains is 2 electrons are remaining here extra. So, OH minus is produced. This is a Bronsted concept. All these definitions represent the acid base concept. So, we also have another definition, that is Lewis concept. It must exhibit a tendency to release electrons, that means it must be electron rich. For example, 2 chlorine atoms can give you chloride ions, and it is 2E minus. Okay. Strong acids and strong bases are those which are dissociated 100% in aqueous solutions. We are going to define what is a strong acid and what is a strong base. Some acids are strong, some acids are weak acids. For example, hydrochloric acid, nitric acid, they are all very strong acids. If they fall on your hands will burn. This HF is a very strong acid, and NaOH is a strong base. Potassium hydroxide is a strong base. Even if if you put NaOH in your hand skin will burn. Even if you put KOH in your hand, skin will burn. So, all the things that are dissociated 100% are called as strong acids and strong bases. We also come across in our day to day life weak acids and weak bases. So, you must be very well aware of the weak acids in our day to day life, isn't it? There is citric acid. So, citric acid is a very weak acid. In all oranges there is citric acid, Mosambi there is citric acid. You put it in your mouth, you will enjoy that. Lemon also has got citric acid. Acetic acid, vinegar, we eat it in the food, we use it for cooking salads and Chinese foods, etc. So, there are lots of weak acids and weak bases around us, and they are those which do not dissociate 100% in aqueous media. So, that is how the definition goes. And salts, we define salts as substances which dissociate partially or 100% in aqueous media. Aqueous media means water. Okay. So, if I take sodium chloride salt, table salt, I put it in water, what it will give? Na plus and Cl minus. Okay. So, if I put this will be totally dissolved. So, totally dissolved means all of it, all the salt that we put in water is contained in as sodium ions and chloride ions. Okay. Then I have what is known as sodium benzoate. this compound C6H5COONase. If it is H here, it is benzoic acid. Now it is benzoate, sodium benzoate. So, sodium benzoate can also dissociate into benzoic acid anion and sodium plus cation. So, all these things you must remember that I have put here, there is an equilibrium sign, here it is one single arrow, correct. So, this single arrow shows that there is no equilibrium, whatever you put is totally ionized. Here in this case it is partially ionized. There is, whenever you put benzoic acid in solution, part of it will dissolve to give you C6H5COO minus and Na plus cation plus some of the undissociated sodium benzoate. Okay. Sodium benzoate is used in lot of pickles, you know, in as a preservative. So, it is a very useful chemical, that is why I have put it here in the slide. This sodium benzoate does not dissolve totally, it dissolves partially. So, a solution of sodium benzoate will contain sodium benzoate, benzoic acid and Na plus ion, benzoic acid anion and sodium plus. There are 3 entities, here it is only 2 entities. Okay. So, coming back to this discussion, consider we are going to write a chemical reaction at a constant temperature. We write A plus B going to C plus D, correct. Reactant A will react with reactant B to give you a product C and another product D. So, the velocity with which the forward reaction goes is proportional to their concentrations. Very fundamental equations and college chemistry still. So, V1 I can write velocity V1 is equal to K1 into A plus B, that is A, I put it here in the bracket, that represents concentration. Lot of people write it as a square bracket also, A and B. So, V1 is equal to K1 into AB, concentration of A multiplied by concentration of B, it is proportional to forward reaction. So, the proportionality constant is K1. So, similarly I can write V2 is equal to K2 into CD, that is reverse reaction. So, C plus D is also going to A plus B now. So, for this reaction I can write another equation like this. Then at equilibrium, what I have, the forward reaction should be equal to backward reaction. So, K1 into AB should be equal to K2 into CD. Okay. So, I am going to write K1 by K2, if they are going on simultaneously and if they are equal, K1 by K2 should be equal to CD by AB. You measure the concentration of the products, divide it by the concentration of the reactants, and you will get another constant that is known as K, that is equilibrium constant. So, actually what it means? It is the concentration of the products divided by the concentration of the reactants. Okay. Again, I must say that it is reactants here, it is not reaction. There is an error in this. Please correct it if you are noting down. Okay. So, I define now another concept, that is activity and activity coefficient. So, here in the previous equation we had written concentrations in their square brackets, is not it? That is equilibrium constant, but it is not actually the concentration calculated from the existing system, but a rigorous thermodynamic equilibrium constant of the reaction tells us that the concentrations are not exactly the same what it should have been. For example, I can write an equation something like this: Ka is equal to A into A plus into multiplied by B in A into B plus divided by AB. So, here I write it is not the concentration, but it is the product. It is the another product related to the concentration, that is known as activity. So, activity is replacing concentration here. Okay. So, here we are going to write an equation like A plus B going to C. So, instead of concentration of Ca and Cb, I have got Cab. Okay. Here it is AB. So, instead of writing Ca, I am going to write Aa plus, that is in concentration of A, I am going to write activity of A into activity of B divided by activity of AB. So, here these things represent the activities of A plus and B minus and AB respectively here in this equation. So, what do? We write activity as a effective concentration of a species. It will not be very different from concentration, but slightly different. But thermodynamically we should not write Ca, concentration terms. So, we define activity as activity is equal to concentration into activity coefficient, that is A plus into this is the activity and activity coefficient is Fa plus. So, that is a notation normally accepted. So, I can write Ka is nothing but concentration of A multiplied by concentration of B divided by AB. Okay, that is for the forward reaction, but they should be multiplied by activity coefficients if I want to do the correct technical representation of the reaction. So, this concentration of A and Fa plus, that will represent activity of A. This and this will represent activity of B, and this will represent AB, that is the product. So, we also define another term, that is I, that is ionic strength. This is very important. It is approximately 0.5 times all the concentrations of all the ions present in the solution and their charge. Z1 is Z is charge, okay, valency of the ions, and this is a very important term which we keep on using in our course regularly. So, 1 to n all. Okay. So, here Ci is the ionic concentration in gram moles molar this thing per gram moles per liter, and Zi is the valency. So, the activity coefficient depends upon the total ionic strength of the solution. For weak electrolytes, activity coefficient approaches unity. For very dilute solutions, activity coefficient becomes unity. So, we are not wrong in writing concentrations as a equilibrium in the equilibrium reactions. Technically speaking, thermodynamically to be correct, we write activity, but very dilute solutions, activity is 1 almost. So, we can write concentrations. So, 99% of the time we use both these systems, and we write this, and activity coefficient depends upon the total ionic strength of the solution. For weak electrolytes, activity coefficient approaches unity, hence Ka and Ka become equal. Here I have written capital A using concentrations, and here it is small a using activity. Okay. So, we continue our discussion regarding the acids and bases a little bit more. So, acid base equilibrium we discuss for the as a next part of our understanding of the basic techniques in chemistry or electrochemical technology. So, I can write for a weak electrolyte such as acetic acid CH3COOH, that is the formula for acetic acid, plus H2O going to H3O plus and CH3COO minus. I can write K is equal to CH3COO minus into H plus and CH3COO minus. Actually, you should notice that I should write H3O plus here, and this is concentration. I should write activity, but we assume that these are all weak acids. So, we can replace weak acids with the concentration terms. So, if 1 gram equivalent of the acid is dissolved in V liters, and if alpha is the degree of dissociation, alpha percent degree of dissociation at equilibrium, then amount of unionized acetic acid, if 1 is this and alpha is the degree of dissociation, undissociated acid will be 1 minus alpha. Alpha is dissociated. So, maximum concentration is 1. So, 1 minus alpha gram equivalent would be the undissociated. So, the amounts of ionized electrolytes will be alpha gram. So, I can write this is alpha. Okay. I can write this is alpha, this is alpha. Okay. So, product I can write 2 of the products concentration, alpha into alpha is alpha square, okay, divided by 1 minus alpha, that is the product, multiple into divided by V. So, or I can say alpha square C divided by 1 minus alpha. So, this is the mathematical expression for weak acids. The value of alpha can be determined experimentally by determining the equivalent conductance of the analytical solution and conductance at infinite dilution. So, the dissociation constants of weak acids are available in databases, and for acetic acid it is about 1.85 into 10 raised to minus 5. We will stop here for this session, and we will continue our discussion on weak bases also, a similar exercise in the next class. Thank you.